Key techniques of monitoring soil erosion with advantages and disadvantages. Soil erosion monitoring can be done through erosion plots, surveying, and traces. However, it is useful to know as much as possible about the hill slope in terms of erodibility, mostly continuous factors, and erosivity, mostly discontinuous factors. Erodibility factors include land use, ploughing and terracing, topography, slope angle and material weight, vegetation, soil properties such as particle size and cohesiveness. Cohesive rocks can have macro feature issues such as joints and cracks, which are further impacted by weathering. They produce spectacular disasters when unstable, such as rockfall. In cohesive rocks, unconsolidated rocks produce alluvial fans, scree slopes, dunes, and debris flows. Erosivity is the effect of running water and precipitation. Drop size and velocity, on average, can be measured. Saturation and pore water pressure varies according to rainfall per season. Saturated soils can lead to mud flows or rotational slump. In saturated through flows, water moves deep into the soil. The effect is slow, but there is a rapid response when saturation point is reached. Dry, arid areas respond differently to saturation. As described by Horton in Overland Flow, the rainfall is first stored in the surface, which leads to sheet flow. Rills and gullies occur when a critical saturation point is reached. Biogeographers look at the degree of instability in hill slope systems according to stresses versus strengths. They measure inputs such as solar radiation, precipitation, and weathering of parent material, and outputs such as percolation, evapotranspiration, and removal of the slope foot. They also take into account trigger mechanisms such as weathering due to rainfall, oversteepening, due to quarrying, and loading. Surveying measures erosion and deposition via leveling, erosion pins, and observations of tree root exposure. It is slower but more methodical. In erosion plots, runoff and erosion from rainfall is monitored through repeated placement of edge troughs along a slope. Advantages are cost-effectiveness, speed, flexibility, and the ability to gain a full picture of the drainage basin. Disadvantages here are siltation and edge effects. Traces are radioisotopes, chemical signatures, and paint. Chemical half-life lets us know how long a substance has been there. However, wet deposition is greater than sedimentation, so cesium deposition is strongly related to local precipitation. Peak concentration is normally at the surface, and traces tell us about clay content and type, organic matter, carbon content, and soil pH. Cesium-137 rapidly fixes to soil particles permanently, so that redistribution of cesium is only due to physical transportation of soil particles. There is no significant movement of the isotope in solution. Thus, increased cesium in an area equates to debris accumulation, while decreased cesium equates to depletion. Unfortunately for the wet, acid upland hills of England, this method is not so precise. Here, the acid soils mobilize cesium into plant root uptake, which has been eaten, moved to new areas, and released in sheep feces. This threshold of erosion-independent movement must be taken into account for this area. Other disadvantages are difficulties in instrumentation, finding a reference value of cesium for the area, and the need to take other isotopes into consideration. Advantages are that it is such a strong emitter, only one sampling is needed. It gives a net effect of erosion and deposition, and the extent and relocation of the erosion, and is a unique tag for studies in the erosion cycle.